Hello and welcome to College Physics 2, Lecture 13, Resistors, Energy, and Power. In the last lecture, we introduced the concept of resistance, that is, the ability for charge to flow through a wire. Here, we're going to start our discussion with an introduction of resistors, which are devices that you put into a circuit to limit the amount of current. In other words, to introduce a very specific amount of resistance into your circuit. Actual resistors, the devices themselves, look like what you see in this middle picture here. These little cylinder-shaped objects are resistors. Now, if you're in my actual physical class, you will use these in lab. You will learn what those colors on them mean. That's basically telling you how big of a resistance there is in each one. And you'll apply them into various circuits. So you'll actually, if you take apart any large circuit or object with a circuit, you'll probably see these devices in there, these resistors. Now, they're used in a number of different ways. On the left, you can see a heating element for a toaster. Basically, all it is a thin enough wire that the current that moves through it is resisted so much that the wire heats up enough to actually cook your food. The defroster in your car windows does this exact same thing as well. And then on the right, you just see a photo resistive sensor. So this is light resisting resistors that turn on your nightlight, for example. So we're going to apply these devices now into circuits, which we've only just basically introduced so far. The simplest possible circuit we could have is simply consisting of a battery and a resistor, or in this case, a light bulb. It's often helpful to just think of a light bulb as a small resistor because that's what they are. It's just a thin filament that happens to resist so much that it glows. And so this is just two components in a single circuit. In our upcoming lectures, we will, of course, see more complex circuits that involve multiple components, potentially multiple paths as well. So one really important assumption going forward is that we're going to use what we call ideal wires. In other words, these are wires with no resistance. This is important. This is very much analogous to, in Physics 1, how we basically always ignored air resistance, because air resistance was typically small enough that ignoring it wouldn't significantly alter our mathematics. And the same is true here. If we ignore the fact that wires do have a small internal resistance, it's not going to be too detrimental to the math that we do. And it makes our lives a lot easier in the process. So we do not consider resistance in our wires, which means the potential at any point along your wire is going to be the same. So in the wire, if you were to draw a graph of potential, like you can see here on the bottom right, potential stays the exact same the entire length of the wire. So in the top part of that image, part A, it shows a wire with a resistor in the middle and then a wire on the right-hand side. So notice in the wire, our potential is staying the same as it traverses through that wire. However, it hits the resistor, and we learned this from Ohm's law, but as you pass through something resistive, your potential is going to drop. Current has to stay the same by law of conservation, so if you increase your resistance, you're going to have to decrease your potential. So as you then pass through this resistor, your potential is going to drop back down. We call this a voltage drop or a decrease in potential. Then it hits the wire again and we stay constant again, right? The potential does not change when you're in your wire. So it's just useful, I think, to often analyze this with a graph because this allows you to better visualize what's actually happening as you traverse the circuit. So ideal wires means there's no resistance, so the potential will stay the same throughout. And we know now that, of course, when you have a resistance, you're going to see your potential drop. It's like dropping down the waterfall in our analogy that we've been using. So right away, let's hop into a basic example just to kind of get a better understanding of all of this. The question says the following. A, which we'll start with here, draw a graph of potential as a function of distance traveled through the circuit, starting at the negative terminal of the battery. So this is basically just saying, draw a graph like you just saw in the previous slide. And we're going to start here at the negative terminal, right? So we're going to start here, and notice the current is flowing in a clockwise direction. So we're going to start by moving up through the battery. Well, think about what happens here when you have a battery. We know that the negative plate of the battery, or the negative terminal, is our 0 point. So there is 0 potential at that negative terminal of the battery. So then when we get up to the top of the battery, if this is a 1.5 volt battery, that means up here we have 1.5 volts. So as we move through the battery, we are going to see our potential increase from 0 at the negative terminal to 1.5 volts at the positive terminal. Then we traverse the wire. So now we're moving through this wire, which we just stated is ideal. That means our potential should stay the same. So everywhere along here should be 1.5 volts. It's staying the same at all points. We then hit the resistor. So now we travel down the resistor. Well, remember, resistors drop your potential. And so in this case, we're going to see a voltage drop back down as we get here. So one way to look at this is that if your potential is 0 at this part of the wire, your potential also has to be 0 here at the bottom part. Then we traverse the bottom wire at 0 volts before we hit the battery again, and this cycle continues. So overall, our graph would look something like this. We start at the negative terminal of the battery with 0 volts. That is our starting point. We move up through the battery. It supplies us with potential, and in this case, 1.5 volts. So our graph is increasing from 0 to 1.5 volts. We then hit the top wire. The wire is ideal, so we do not change our potential, meaning we stay at 1.5 volts, until we hit the resistor. Once we hit the resistor, we have a voltage drop that takes us back down to 0. We then move through the bottom wire, where potential stays at 0, before we come back. So basically what happens now, once you're at the end of that bottom wire, it basically just takes you back to the start, and now the battery's going to lift those charges back up to a higher potential. And so the charges are going to move up in potential, then drop, then move up in potential and drop. And they're going to keep doing this over and over until the battery runs out of its chemicals. Once that happens, then your supply of energy for your charges shuts down and the whole circuit stops working. So that's what our graph would look like. Now there is a part B to this problem, which asks for you to determine the current in the circuit. Thankfully, it's very simple for this problem. Unfortunately, it's going to get a lot more complicated when we get to bigger circuits. So it's good to just be able to apply it in a basic sense for now. We have an equation that we introduced in our previous lecture of Ohm's law. The most common way of writing Ohm's law, at least the way I normally see it, is delta V equals I times R. We want to solve for current, so that being I, so that would give us delta V over R. We do know both of these values. The problem shows us that the battery's potential, or EMF, is 1.5 volts, and the resistance is 15 ohms. So we have 1.5 volts over 15 ohms. This gives you 0.1 amps, or a tenth of an amp. Now, sometimes students still have an issue, of course, with the fact that this is labeled as epsilon, and I plugged that in here for delta V. Remember from our previous lecture that epsilon, the EMF, is by definition the potential difference. It just is what we call the potential difference of a battery. So just to be clear, delta V of the battery is your EMF. So that is what we plug in here as the 1.5 volts. Okay. Well, with this, we can then get into our discussion of energy and power. We did introduce the concept of energy a little bit in our previous lecture, but now we're going to take it a step further. We're going to look at how energy changes throughout the entire path around this circuit, and then look at how that relates to power. So now, let's go through this discussion of traveling around the circuit again, starting at the negative terminal of the battery. This time, though, discussing what's going to happen in terms of energy. At the negative plate, or the negative terminal of the battery, there is no potential and no potential energy. But then the charges are lifted up through the battery to a higher potential. This is supplied by the chemicals and the chemical reactions that are occurring inside of that battery cell. So everything in this process starts as that chemical energy that is stored in the battery. Those chemicals are then used to lift your charges up to a higher electric potential energy. In other words, chemical energy, E, chem, is being transformed into electric potential energy, U. We had an equation for this in the past. Delta U is equal to Q times delta V. In other words, delta U is equal to Q times epsilon. So that's just describing to you how much energy they're gaining as they're moving through the battery. So that's what's happening, right? We're using chemical energy to turn that into electric potential energy at the top of the battery. Well, then we move through the wires. So this is driving motion of charges. Well, the energy that describes motion is kinetic energy. So once we have our potential energy up at the top of the battery, that transforms into kinetic energy, motion of the charges. Those charges then move and hit the resistor. Well, resistors, it's in the name, resist things, so there's going to be friction involved. That friction between the charges flowing through the resistor and the resistor itself causes your objects to slow down. But remember, that means you're losing kinetic energy. But that energy has to go somewhere. It can't just disappear because of conservation of energy. So as your charges are slowing down a little bit or being experiencing friction, they are losing that energy to heat or thermal energy. Again, think of a light bulb. That tiny little filament in your light bulb heats up so much that you can feel the warmth and see it glow. So overall, we have a decently sized chain of reactions in terms of energy in a circuit. It starts as chemical energy in the battery. That supplies your charges in the battery with potential energy. That potential energy is then used to drive the motion of the charges, in other words, giving them kinetic energy to move. And then that motion passes them through the resistor, where that energy is dissipated as heat or thermal energy. So once you do that, then the process starts over again. You're back at the terminal of the battery, getting a supply from those chemicals, and it just keeps going until the battery runs out. Because once your battery runs out of its chemicals, then you shut down the first part of this chain reaction, and then everything else shuts down in the process. So that's your basic look at how energy transforms throughout a circuit. Now, this brings us to power. I don't believe I ever introduced the concept of power in Physics 1. Our course usually ends in just enough time for us to get through all the main topics of energy itself. Power, quite simply, is the rate at which energy is transferring. In other words, it's the amount of energy per unit time. So that would be energy over time if you wanted to see it mathematically, which you will, whether you want to or not, because we're about to show that. But the idea is it's going to be the amount of energy in the amount of time. In terms of the units, energy is measured in joules, time is measured in seconds. So the units of this would be the joule per second. But we give this a new name called watts. So that's why we say, like, if you have a 60-watt light bulb, that's what you're really learning about. It's telling you how much energy in joules it's going to pass every second. So the equation for this, it's the amount of energy that's changing over the amount of time. So in a battery, we are going to gain a certain amount of potential energy, right? In the battery, our charges are gaining potential energy in some amount of time, delta T. Well, remember that we just showed an equation, and it was from a previous lecture, that your change in energy is equal to your change in charge times epsilon. So if you wanted to simplify this equation from what it is right now, just think about what you're seeing here. We have delta Q over delta T. That together, delta Q over delta T, is by definition current, I. So this equation for the power supplied by a battery is simply the current I times the EMF of the battery itself. In other words, its potential difference. I refer to this equation as pi. I don't make my students memorize formulas, but if you ever had to, it's an easy way to remember this one, pi. Power is equal to current I times the epsilon, or EMF, of the battery. So that's just a way to describe the power supplied by a battery. There's also a way to describe the power dissipated by a resistor. And so it's a very similar process. Here we have power is equal to I times the potential difference of the battery. Well, here it's I times the potential difference of the resistor. Same exact equation. Notice how they have the similar form. So this is alone here. This on its own is a helpful equation. P equals I times delta V. That'll allow you to calculate the power, assuming you know the current I and the potential difference delta V. Well, that's not always the case though, right? Sometimes you know the resistance, or instead, maybe you don't know what the potential difference is, or you don't know what the current is. Well, luckily, we have Ohm's law. So let's say you take this equation, you keep I, but you replace delta V with I times R from Ohm's law. Well, that gives you I squared times R. Or, instead, take this first equation again, swap out I for delta V over R. And then you still have your delta V left over. Well, that gives you delta V squared over R. So the point is, you have three different ways to express the same equation for power that is dissipated in a resistor. I times delta V, I squared times R, or delta V squared over R. I think this is the first time we've ever had an equation with multiple forms that work for it. So just be aware that you don't have to know every single one of these. You just pick one of these three to solve for your power. So if you know the current I and the potential difference delta V, then use that form of the equation. If you know I and R, use the second form of the equation. And if you know delta V and R, use the third form. If, for whatever reason, you know all three quantities, then just pick one, whichever one. All right, so with this, let's do one more example before we conclude this lecture. The problem states the following. An electric kettle has a coiled wire inside that dissipates power when it carries a current, warming the water inside. Sort of like a toaster. It's got a coil inside that basically just heats up with the passage of current. So a kettle designed for use in England carries a current of 13 amps when connected to a 230 volt outlet. Note here in the US we use 120 volt outlet, so theirs is a bit different than ours. Anyways, what is the resistance of the wire, and what power does it dissipate as it's running? So obviously, let's start in order. Let's go with part A. We want to figure out the resistance of the wire. So we can either use the definition of resistance, rho L over A, that we introduced last time, or we can use Ohm's law. Well, we can't use rho L over A because we actually don't know any of those three numbers. Rho is what the material is made out of, which we don't know. L is the length of the wire, which we don't know. And A is the cross-section area of the wire, which we don't know. So clearly that equation will not apply, which means we invoke the use of Ohm's law. We want to solve for the resistance R, so that becomes delta V over I. We do know both of these numbers given in the context of the problem. We know we have 230 volts divided by a current of 13 amps. Overall, this gives you a value of 18 ohms. So we have a resistance of 18 ohms, which we can now use if we wanted to solve for the last part of this problem, what the power dissipated is. Well, here's that interesting scenario. We know the current I, we know the potential difference, delta V, and we now know the resistance R. In other words, we know all three of the main components of these types of problems. We know delta V, I, and R. What that means is you can solve this using any of the power options. You could use I times delta V, or I squared times R, or delta V squared over R, because all of those are perfectly valid. My one recommendation, though, for choosing the equation is to pick the one where you didn't already make up one of the numbers. In other words, we had to figure out what R was. We could have been wrong, right? Maybe I made a mistake. So I probably wouldn't want to choose the equation with an R in it if there's one without that, because I don't want to have to worry about using a number I got incorrectly beforehand. So why don't we just use I times delta V? The current is 13 amps. The potential difference is 230 volts. Putting this all together with some rounding, you get 3 times 10 to the 3 watts. And that's your answer. So again, even though I crossed them out, both of those equations would have absolutely worked and gotten you the same answer, so long as you got the first part correct. So that can be helpful, at least for these problems, in the sense that you have multiple options for the right equation. All right. Well, to leave you, I'll just put up this summary slide. I'm not going to read it all for you here, but it does do a good job of summarizing all the key points from this set of lectures. So the last 2 lectures, I believe, where we talked about what current is, what an EMF is, how energy works in these circuits, and things like that. For this one, I don't have any end of lecture questions, so that'll take us now into a deeper discussion on circuits coming up. As always, thanks for watching and have a great day.